Very happy this week to have Anders Hansen from the University of Cambridge. So Anders' background is in functional and harmonic analysis, and his recent work includes generalizability of neural networks. He's currently a reader in mathematics at the University of Cambridge and also professor of mathematics at the University of Oslo. He has won several awards. So in 2012, he won a Royal Society University Research Fellowship. In 2017, the Leverhulme Prize. 2018, an IMA Prize, and in 2019, the Whitehead Prize. Today, he's going to be talking about the foundations of computational mathematics, Smale's 18th problem, and the potential limits of AI. I believe some of Anders' students are in attendance, and they are here to help answer some of the questions. So please feel free to ask questions during the chat, and either someone will answer them in the chat, or I'll ask them directly to Anders. I think that's probably everything I want to say. So with that, I'll hand over to you, Anders.
Well, thanks very much. Thanks so much for having me. I'm thrilled to be here to talk about foundations, which is one of my real babies. I'm also going to be talking about Smale's 18th problem. That's not a complete coincidence. But I do want to point out that it's actually Steve Smale's 90th birthday today. So happy birthday to Steve from all of us. Anyway, so this is joint work with Ben Adcock, Vegard Antun, Alex Bastunis, Matt Colbrook, Nina Gottschling, Clarice Poon, Francesco Renna, Laura Thiesing, Werner Vlacic. And I want to start with a slide where I essentially set out the main goals of this program, which is to determine the foundations of AI and deep learning, but also the potential limitations of them. And in fact, Smale's 18th problem on the list of mathematical problems for the 21st century is exactly on the limitations of AI. I'm going to describe that problem in detail a little later on. But before I argue why we need this foundations program for AI, I want to say a little bit about deep learning and its standing in the sciences. And I want to mention what everybody knows. This is so well documented now that the impact of deep learning is completely unprecedented. And if I were to list the areas in the sciences for which deep learning is now used, I would probably save time if I listed the complement instead, suggesting how unprecedented the situation is. But with this impact, there's also a substantial enthusiasm and optimism. And this is symbolized by this quote from Geoffrey Hinton from 2017, where he says they should stop training radiologists now. I'm not going to get into the debate regarding if that's a good idea or not, but I do want to point out this optimism, and I want to make a comparison with the optimism that was in the early 20th century regarding mathematics. And I want to compare this a little later on, and that's why I want to set this tone with this quote from Hinton. Now, when we're going to be talking about foundations, we will also have to talk about the research methodology. And I want to point out that, of course, we're not the first ones to essentially argue that we need a debate about the research methodology. And I think that Ali Rahimi made a very good point and essentially put this in perspective in 2017. He likened the modern machine learning research methodology to alchemy. This is something that not everybody shares that view. As you can see on my slide. However, I do think it's worthwhile essentially looking at what the alchemists did and learn a bit from that research methodology. The research methodology of the alchemists was essentially you have a pot and you add a little bit of green and then you add a little bit of yellow and you stir. And they were hoping to create gold, which they of course were not able to do. The important thing is that if you add a little bit of green and a little bit of yellow and stir and you don't create gold, you can simply try this again and add a little bit of black, and then you add a little bit of brown and you add a little bit of red again and you stir, and you can continue this process. But this essentially, these iterations will never end. And the point is that that research methodology would never be able to determine its own limitation. You will never be able to find out that you cannot create gold with that research methodology. And hence, you need a foundations program to essentially figure out the limitations, the cases for which you cannot create gold. And that's essentially what this argument about having a foundations program is about. So I want to use one particular issue in modern AI and deep learning as the main motivation for this, because it's also a practical problem. And that's the Achilles heel of the whole methodology, which is that it is universally unstable. And I'm not going to go through the vast literature on papers that document this and also try to solve this. I want to show you a couple of papers that I think would be of interest. And I'm going to start with this paper here, which was published in Science Magazine a little more than a year ago. And what is also important to emphasize is that this is not written by grumpy mathematicians like myself, but from people in the medical profession. This is a collection of very fine researchers from Harvard Medical School and MIT, and these are people in the medical professions. And I want to show you this figure here that I think illustrates what's going on very well. So this figure that you have on the top here is essentially on automatic diagnosis in medicine. And here is where you train a neural network to do cancer detection or cancer diagnosis automatically. So what you do is that you train your neural network to figure out if a mole here is benign or malignant. And this here was actually based on a paper, I think that came out in 2018, I think. It was a Stanford crew that did this, and they showed that they could train neural networks that did very well on diagnosis with moles. The problem, however, is that you can add a little bit of noise here. And so the noise is so small that these images here are, to the human eye, completely identical. But the neural net is going to go from being very confident in one direction to being completely confident in the other direction. You can also do rotations, for example, and you can also do the same thing for text analysis. You essentially substitute some synonyms so that the text has the same meaning for a human, but the neural network is going to give a completely different interpretation. So there's a whole myriad of these things now. And what I do want to point out is that it becomes also a safety issue. And this paper, the Science Magazine paper that I just showed you, was also written as a response to the fact that the FDA, the American Food and Drug Administration, for the first time in history, allowed or certified AI and deep learning methods for automatic diagnosis in medicine. So this is only for early detection of diabetes, but it is likely that more of these things will come. And I wanted to show you the end of the paper, the Science Magazine paper written by the previous mentioned researchers. And I want to highlight this quote here that suggests an essential question remains: when and how to intervene. So the reason why I want to point this out is that these are concerns made by people in the business. These are not concerns made by mathematicians. So that's about the instability problem, typically in the medical sciences. Another area for which is also very close related to the medical sciences is medical imaging. And there was a very fascinating paper published in Nature in 2018, where there's sort of a new methodology suggested for MRI. Learning the physics is, in some sense, the main message of this paper, where the idea is that you use a fully connected neural network to learn from the Fourier measurements how you can sort of invert the MRI machine. And there was a follow-up research highlight paper on this in Nature Methods, and I think the title says it all: AI transforms image reconstruction. It also suggests that it will improve the speed, accuracy, and robustness of biomedical image reconstruction. It's worth noting, I think, that it's a pretty bold claim to suggest that it's going to be robust, given that there is a vast literature on how unstable deep learning is in general in other areas of sciences. And hence it's a legitimate question to essentially ask if this really holds, and it's legitimate to run a test on it. And that one can do. So here is this, the method published in Nature. It's called AUTOMAP. And what it does is that you'll have an original image here. The original image then goes through the MRI machine. You get Fourier coefficients. In this experiment here, there is essentially 60% subsampling, so it's about 2 times speed up. And this is the reconstruction that you'll get with the AUTOMAP network. If it's really true that it's stable, then you should be able to take just tiny perturbations here, and then the neural network through the Fourier transform is going to take that and then create a new reconstruction, which should not be too far away from the original. And what you see here to the left-hand side is the noise in the image, and to the right-hand side, it is the effect of that under the reconstruction method AUTOMAP. So as you see, tiny little perturbations to the left yields enormous results in and errors in the right-hand side. So despite the grand claims, this is a completely unstable neural network. And you can, of course, ask if it's because of a sort of inherent instability in the problem itself. And if you test this against the state-of-the-art method, you see that that's not affected. However, I do want to mention that what you see here in the state of the art is based on that particular noise, which is created to be a worst case scenario for this. So I want to point out that you could essentially ask, you should do a worst case scenario for some of the other methods. And we're going to discuss that a little later in the talk. I just want to point that out. But to be fair to the AUTOMAP team, this is not something which is exclusive for their network. This turns out to be quite universal. And here is another neural network. This is created by some very fine researchers at Imperial College London. It's the same thing, completely different setup, completely different architecture, still an MRI problem. This is 25% subsampling. You take tiny perturbations to the left, this is the original, and you'll see what happens to the right. As you'll see here, it's actually very hard for the human eye to see the differences here to the left. You can see tiny things here, but you can actually deform the image completely. This type of image is not dangerous. The radiologist is obviously going to say that this here is non-physical immediately. The ones that are dangerous are these. So look what happens now when I make a tiny little perturbation to the left. Can you see here now suddenly you get this shade here? That's a false positive, which is very hard for radiologists to say, oh, is this actually something which is non-physical? So these are the dangerous ones. I'm going to show you some other cases of that later on. Anyway, so for those who are interested in the details, have a look at this paper here. It was published in May. That has tons of other experiments with other neural networks and essentially concludes that you have sort of a universal phenomenon in this. And I'm going to get into the theory and the foundational results of it later on. I do want to point out that when this paper came out, there was quite a lot of press interest because, well, it concludes that AI techniques in medical imaging may lead to incorrect diagnosis. And you could get the feeling that this was somewhat of a surprise, but I think it's fair to say, and one should give credit to people in the medical profession that I think saw this coming. And I want to point out particularly a tweet by Kurt Langlotz, who's the director of the Center for Artificial Intelligence in Medicine and Imaging at Stanford. And his tweet as a reaction to the press release of this paper was confirming what many believed about deep learning image reconstruction. So I do think that this was a valid concern that did exist in the community before this paper was published. So why has the instability problem in deep learning not been solved? And you see, what I wanted to do now was to give you the motivation for this, that essentially this instability problem is a serious one, and it's not just of mathematical interest, it is of interest because people are worried in the sciences. And it's not the case that people haven't tried to solve this problem. There's tons of papers out there and tons of different attempts, but it's still an open problem. And the question is why? And here is where we want to draw a little parallel to what happened in the early 20th century in mathematics. What happened at the time was that the foundations of mathematics were actually not established at all, and Hilbert was the one who led that program that became known as Hilbert's program. And that was the birth of modern logic and birth, in some sense, also of modern computer science. And Hilbert was very optimistic. Hilbert believed that maths could solve everything. And he also believed that computers compute everything. And this optimism, which is quite similar to the optimism that we see now in AI and deep learning, and I think that it's a fair comparison. And the fact that Hilbert was a great optimist in this, but in some sense was also wrong, doesn't make him any less of a mathematician. He's one of the greatest mathematicians ever. He's one of my great heroes. But it's allowed to be optimistic, but also realistic later on if there are lower bounds. And you could see his optimism, particularly in Hilbert's 10th problem. So Hilbert created a list of 23 problems with great mathematical problems for the 20th century. The 10th problems is as follows. Find an algorithm to determine whether a given polynomial Diophantine equation with integer coefficients has an integer solution. I'm not going to get into the details of this. The only thing I want to highlight here is the beginning of the problem. It is find an algorithm. Hilbert didn't even suggest that it could be the case that you couldn't find an algorithm. He was convinced that the problem is just to find. There does exist one, it's just finding it, which essentially emphasizes the optimism that he had about what algorithms could do. But what happened was that Gödel and Turing essentially turned Hilbert's optimism completely upside down and Gödel showed that, well, roughly, I'm not phrasing this in logic terminology at all. This is in layman terms. He showed that, well, there are true statements in mathematics that cannot be proven. And Turing showed that there are problems in computer science that cannot be solved with a computer. And this went completely against, essentially, Hilbert's original beliefs. So it turned Gödel and Turing into the ultimate party poopers of the century. But I do want to point out that it didn't slow down mathematics, nor did it actually put any restrictions on the use of mathematics, nor computer science. It actually created a vast field on understanding the foundations. But particularly the impact that Turing had on shaping the field of computer science is completely essential, because computer science was a field that was established very well aware of its limitations from the get-go. And the irony is that the solution to Hilbert's problem, which suggested find an algorithm, well, the solution to that, which took about 7 decades, is that no algorithm exists. This is a famous non-computable problem. So that leads us to the question about foundations and the foundations program that I'm arguing that we need in AI. But I want to point out that this is actually already very much rooted in mathematics. And Hilbert made a list of problems for the 20th century. And Smale created a list of problems for the 21st century as a response to Vladimir Arnold. And his 18th problem is, what are the limits of artificial intelligence? So this is essentially a great tradition in mathematics to talk about the foundations of artificial intelligence. And what I'm arguing now is that we really need the community to focus on a program like this. And a program will need to have theorems that are of two sorts. One is universal boundaries. That will be the types of you cannot create gold. And there's also going to be boundaries of the methodology. That means that you may be able to make X with method Y, but you may not be able to do this, say, with another method. So you need to find out what kind of boundaries there are on the methodology that you're using. And I'm going to show lower bounds on both of these, both lower bounds that are universal and bounds on the current methodology. So that was essentially most of the motivation. And now we're going to get into the more nitty-gritty stuff with details in mathematics. And I want to start with a little bit of definitions. I'm going to use NN here, typically standing for neural networks. Occasionally, we'll put in the dimensions needed. Here is the standard definition that you all know very well. bunch of affine mappings separated with some nonlinearity. I do want to point out that there are now many other more general definitions of neural networks out there, but that is not going to be relevant to what we're doing. All the lower bounds that I'm going to suggest are going to be universal also for these definitions, and for the upper bounds it will be true for these more classical definitions. So this is not really essential for the foundations. Okay, so let me start with the first theorem. And the first theorem here addresses essentially the question, should we expect instabilities in deep learning? And what this theorem here shows is that absolutely you should. And it's not only that, it's the actual methodology that encourages the instabilities. So what this theorem says is that there's uncountably many classification functions out there, decision problems, for which you'll have the following phenomenon. Choose your neural network dimensions. They can be as large as you want. This has nothing to do with restrictions on the neural networks. They can be as big and fancy as you want, and you'll have the same phenomenon. The number of layers here are going to be greater than or equal to 2. And here, this epsilon parameter, this is going to be the one that essentially determines the instability. The smaller that epsilon is, the more unstable the problem is. And this can be arbitrarily small. It should be less than 1 over k plus m. K is going to be the size of the training data, and m is going to be the size of the test data. And m can be arbitrarily large. And then what's going to happen is that you'll now have uncountably many training sets and classification or test sets. So you have the following phenomenon. If you now train your neural network with your favorite cost function, then what's going to happen is that you will have 100% success rate, both of the training data and the test data. So fantastic performance. And mind you, the m, the size of the test set, could be arbitrarily large. But while you have that great success, you also have uncountably many cases for which the neural network is going to misclassify. And those cases are just epsilon away from the training data. So in other words, you've seen this before, you're epsilon away from it, and that epsilon is arbitrarily small. So you can get essentially arbitrarily instabilities. And what you see here is that this is essentially caused by this problem here. It's the methodology that causes this, because, and here's the paradox, there does exist another neural network, not the guy that we're seeking here, another guy for which you actually get the same performance, but you also have stability on the ball. And that is an important question, or that yields an important question. That is, why on earth are we getting the bad guy? Why don't we get the good guy? We can show that the good guy exists. And this is a big problem, because the point is that we can prove so many theorems about how great neural nets are, and they're fantastic. And there's a very vibrant and great tradition in this in approximation theory up to the 2000s, and then now sort of the rebirth of this after 2012. And there's so many different types of approximation theorems. So this is the universal one, which everybody knows. And essentially it says that you can do anything with deep learning, or with neural network rather. And the question is, what does actually that tell us? Because is it really the case that I can compute them? If you tell me that there exists a neural network, can I always compute it? And you see, now we're getting back to this issue of Hilbert and Turing. Will there always exist an algorithm that can do the job? And that's what we're going to get into. And we'll see that this is actually a very, very delicate problem. So I'm going to try to phrase this mathematically. So what we're essentially asking now is that if I have a neural network that exists, so it's a function of some training data, can I find an algorithm that computes that neural network from that data? So in other words, suppose I have omega here is now a collection of training data, some xj's. And for each of these collections of training data, one can prove that there exists some neural network. Let's call it phi of iota, with certain properties. So in particular, you know that there's a map map, let's call it kappa, it takes now the elements, the training data, and spits out a neural network. And the question now is, can I find an algorithm that takes the same input and spits out the neural network? Or maybe it doesn't do that. Maybe I can only get approximation. But to which accuracy can I get that approximation? So you see, this is now essentially a type of question that Hilbert could have asked, just like he asked about the 10th problem and the Diophantine equations. But now we can essentially see that this is quite delicate. So I want to avoid constructing bizarre mappings that you've never seen. We want to, here in this case here, take some what I would call standard mappings that people know very well in mathematics of information and optimization. You've seen them so many times before. This is typically the basis pursuit problem. This is called lasso. You can put a square here or take out the square. This is sometimes referred to as square root lasso. And these are the three different types of problems that I'm going to look at. And what we're going to show is that you can actually find neural networks that will essentially interpolate these mappings. I'm going to call psi of A and Y here. That's the solution mapping, if you will. That's a set of minimizers here. So you take a matrix in and a vector Y, and you get the argument, and that's going to be denoted by this capital Xi. Okay. Now, if I'm given some A, matrix A, and a bunch of Y's, then if I'm going to do some training on this and ask if I can actually do this on a computer, I have to be a little careful. Because if we really talk about a computer here, it has to be a digital computer in terms of a Turing machine. I'm not going to get into the details of what that is, but the point is that an actual computer can only work with rational numbers. And that means that if you have irrational numbers, like if this A here was the discrete Fourier transform, which it could very well be in an inverse problem, then I cannot see A, but I can get it to arbitrary precision. So the fact that we're approximating things on a daily basis is one, because we have irrational numbers, but also because we're running floats. So if you are running floats, which you're going to be doing in 99.9999% of the cases, that means that even a number like 1/3 is not represented like an integer pair 1 and 3. It's represented as an approximation in base 2. So that means that everything which is not even a base 2 number will be approximated. So if you're going to talk about being able to compute something, it has to be computed from approximations. So the best thing that you can hope for are collections of approximations to whatever accuracy you want. The norm here is completely irrelevant. The norms are equivalent anyway. So you can get this to whatever precision you want. And also the solution to the problem. You should be able to get to the precision you want. So this is now essentially the training data that you're given. And I'm going to call omega, that's typically going to be the collection of elements of the matrix and the inputs y's. And then this family here will be associated with some training data of this form. I'm going to denote that with omega t. And then when you have this setup, we can now prove things. We can prove that for all of these problems, there is, for any collection of inputs, that's important, any collection, with the corresponding data, the training sets that I just described, there will exist a mapping that takes the training data into a neural network. And this neural network is going to be great. It's actually going to give me the mapping. It's awesome. And showing this is not hard. This is just essentially cut and paste from off-the-shelf theorem that exists, and it's not, what should I say, a great mathematical achievement. And the purpose of this is not to essentially create something regarding the power of neural networks. It is essentially to set this up. Now, we've shown the existence of neural networks from this training data. The question is, can you compute them? And here is the theorem, which is much more interesting. So what this theorem says is essentially that you can have all kinds of things going on. It's a little cumbersome, so I want to tell you what's going on rather than sort of read it out loud. And what it says, take any of these problems, for which you do know that there is a neural network that exists for any omega. Choose now k to be greater than or equal to 2. That's going to be the number of correct digits. And L is going to be a number, which is going to be the number of samples. And then what this theorem says is that there exists a collection of inputs, omegas. And the important thing is that this omega here, it's the same for all the statements in this theorem. And the first one, it says that there does not exist any algorithm that, given the training data, can produce a neural network that approximates this mapping here to better than k correct digits, even though we know there exists one, but no algorithm can do it. And it's also important to emphasize that you can't do this even with a randomized algorithm. A randomized algorithm is not going to do better than coin flipping in this. And we all know how important randomization and stochastic algorithms are in the training of neural networks, but that's not going to help you. Now comes the first paradox. However, if you're a little less greedy, and you don't want k correct digits, but you want k minus 1, so a little less accuracy, one less digit, then there does exist an algorithm that, with this training data, can produce a neural network that actually gives you the mapping to k minus 1 digits. However, any algorithm, and that means also any random algorithm, is going to essentially need arbitrarily many points in the training data. So they're going to use arbitrarily many samples to create this neural network. And this is going to happen with a probability that's now going to grow with the dimensions. You get arbitrarily close to 1. So what it tells you is that, yes, you can do this, but there will be inputs for which you won't be able to deal with because it's going to require too much data. And now the third paradox is that if you're a little less greedy and only require k minus 2, then k minus 2 correct digits, then you can do it with a deterministic algorithm, and you need only L samples. And to essentially sum up what this theorem shows is what can actually happen even if you're only interested in, getting k digits, k minus 1, or k minus 2. And of course, this issue of having k being greater than or equal to 2 is only so that you can have this k minus 1, k minus 2 effect. If you're only considering this part here, k could be 1. And it's not that we have cheated in this business here. All of these classes here are well conditioned. I don't have the time to go into all the condition numbers here, but it's not like we have given you essentially a cheating point here for which we actually give you ill-conditioned problems. So to sum up what is going on here is that the answer to that problem, or to that question rather, can neural networks be trained? Not in any way in general. There will have to be very specific reasons why you have to do that. So there are basic mappings for which you can interpolate by neural networks, but you will never be able to actually compute these neural networks. And that means that there is a fundamental restriction. This is a universal bound, like I talked about. This is not about the methodology. No algorithm can do this. And that means that there will be restrictions on what a theorem that says something about the existence of a neural network, what that can actually say in applications. Because you might be able to say that there exists a neural network that can do great things, but you may not be able to compute it. And there are 3 things that can go on typically. One is that no algorithm can do it. The second one is that there exists an algorithm that can do it, but it's going to simply take too much training data to pull it off. And of course, it could be the cases for which you can do it, and that's the case which you want to be in, but that is never automatic. So if you're interested, the paper is coming out soon, so that has all the details. There's more theorems on the foundations here, and I hope you will like the paper when it comes out. I want to make a little comment regarding the...
Anders, can I just
yes.
interrupt you? A couple of questions.
Oh, shoot.
Okay, your students have just answered these questions as I speak. But maybe I'll pose them to you. And
yes. Should I go back to the theorem?
Yeah, please.
Yes.
Someone's asking is, does the explanation work for a convolutional neural network where an autoencoder is selected rather than through training?
This is universal. It has nothing to do. It just says that there exists a neural network that can interpolate, but no algorithm will be able to do this for all inputs. So it has nothing to, this has nothing to do with the design of the neural network. It's not like you can circumvent the theorem like this result by saying, oh, I'm going to have a different architecture or anything like that. This is not a methodological restriction. This is a fundamental barrier, just like the halting problem is a fundamental barrier that Turing showed. This, by the way, has nothing to do with, this is actually a curiosity that I think some people would appreciate. If I add an oracle on the algorithm that could solve the halting problem, it still wouldn't be solvable. So this has nothing to do with an architecture. This is a completely universal bound that is, what should I say there, in stone. It has nothing to do with architectures or any tricks that you can sort of circumvent it, if that makes sense.
Another question is how, so I'm saying it's not quite clear how K is chosen for some examples. So is the theorem is for any K?
Any K. So here is the point. There will exist, so this is actually a very good point. This is, we should get that straight. It says any K. So for any K, the K can be 2 or K could be 59. You will have inputs for which you'll have this phenomenon. So if I choose K to be 5, there exists now a collection of problems for which you know there exists a neural network that can actually do the job, but no algorithm can compute those to 5 digits. But there does exist one that can do that to 4 digits, but there will be inputs there for which you can never train because you will need too much data points to get there. So this is super important. The K here, that's what dictates the omega. So you choose the K, then there exists an omega. But the previous guy here says that for any collection, there exists a neural network. So you choose the K, then I tell you that there is an omega, and then we have the other theorem says that regardless of the omega, there exists neural networks that do the job. They're awesome, yes. And this theorem then says, but no, actually for the K you chosen here, this is not gonna work, but you can get it for K minus 1, and for K minus 2, you need few samples. So this is the paradox that we want to show to illustrate essentially what can go wrong. And what I'm going to conjecture in one slide is that it's actually typically what happens is a lot, in this case here, that you need too much data. That is what is happening. That's what we're actually seeing. I cannot prove that for all existing problems yet, but I hope that I'll be able to prove that for some soon.
Yeah, thank you very much. There are more questions, but your students are doing a very good job answering them. So I'll let you continue.
Excellent, very good, very good. I should say also that, you know, this is sort of Matt's baby, so I'm sure that he's very happy to answer questions on it. Where was I? Yes, the conjecture. So I conjecture simply that the reason why we haven't solved the instability issue in image classification is because of the second case, that you need too much training data. And of course, this is not well defined at all, this conjecture, and it's not well defined simply because I cannot mathematically describe the question, is there a cat in the image? But what I can do is that I can write down very simple problems in image classification for which I can write down. And what we're working on now is to show that there is a lower limit to essentially how many samples or how many training data you need to see with the current methodology. And that's the barrier, but I hope to report on that in the future. Okay, but now I'm going to get to another barrier, and that is why DL is unstable in inverse problems, and that's completely different. That has nothing to do with the reason why it's unsolved in classification. And I need to set this up, so I need to go through a little bit of the basic setup. I want to solve a underdetermined linear system. And of course, that means that I can't have a sort of inverse for that A for the whole class, for the whole vector space. That's nonsense. So I need to restrict myself to some domain. I'm calling it M1. And then I have a range of A acting on M1. That's going to be where the Y's live, the measurements. And I'm interested in now recovering the X's from the Y's. The Y's live in M2. And the way this is typically done is that you take your favorite training set with your xj's, they live now in M1, and then you have automatically that the measurements, let's call them yj's, are the A xj's. And you simply solve an optimization problem for which you're essentially trying to fit a neural network so that it essentially sends the measurements to something close to x1 or xj rather, and you do that by solving this problem here. There's tons of different cost functions. This is popular. This is, for example, the one that's used in AUTOMAP, the one the Nature publication, but there could be tons of other ones. What actually happens typically is that if you now train, you will recover x from ax with a little bit of a perturbation. But that perturbation should be small. And the whole idea is that, well, if you can't do this with a small perturbation on the training set, how do you think you're going to do well on the test set later on? So this is crucial. So we call that essentially small error on training data. And this is what causes everything. Because now I'm going to show you a universal instability theorem. It has the universality because it's not restricted to any neural network. It is about any mapping that's going to recover y's from the x's. Sorry, it's going to require recover x's from the y's, or the ax, if you will. And what this theorem says is that you only need to have that it recovers, through a recovery method, recovers two vectors x and x prime well. And at the same time, the x and x prime that could be far apart are sent close to each other through A. And this is typically what happens when A has the non-trivial kernel. And then if that happens, all hell breaks loose. But you see, this is a very, very simple linear algebra argument that you can picture in your head. Suppose that x and x prime are far apart, right? And now A sends them to something which is close. And you now have a method that works well on both of these guys. That means that it takes something that is close to something which is far apart. That is instability. And that means that you get the local Lipschitz constant. It can blow up. It can be arbitrarily big, of course, depending on now how far x and x prime were and how small this eta was. And you will also have false positives. For example, there's a brain tumor that you add that shouldn't be in the image. I'm going to show you some examples later on. Or there is a brain tumor in the image for which you remove. And this is essentially the cardinal sin, which is described by this theorem here, recovering things that are too close to the null space. And that's why you get the instabilities. And what you can ask now is, well, so you show that this happens, but does it happen often? And the point here is that these things are not rare events. And the reason why is what you see here in this theorem is that it holds for balls. There's balls around each point where this happens. And that means that if I now have a perturbation in the form of some random variable, I don't need a lot of assumptions on this. It can be a Gaussian, for example, because if now this random variable is going to essentially hit a ball with some probability, well, that's also going to be what happens, or it's going to give us the instabilities. So I can now use the previous theorem and say, well, actually, with very mild assumptions on this perturbation here, the random variable, the false positive and the false negatives are going to happen with some probability that it's greater than 0. And you can estimate this. You can put more restrictions on this and analyze this back and forth. We'll do a little bit of that in the paper. I'm going to refer to that in a second. But in general, it's very hard to estimate what these things are, but they will be greater than 0. So the only way to test this, if you don't have any analysis of your neural network, is simply try it. You can do that. I'm going to show you a very simple test. This is the Deep MRI neural network that I've shown you before. This is the one that's created by these fine researchers at Imperial College. It's the same image. What you see here is V1 is the true image, well, the cropped one, added a little bit of a noise. That V1 is chosen from the 100 trials of Gaussian noise. and we picked the worst one in the actual recovery. And you'll see that it's actually tiny. It's very, very little noise in this image here. And this is the outcome of this deep MRI neural network. And you see here how it introduces this false positive. There's a hole that should not be there at all. And this V2 is the worst out of 20, and V3 is, that's just one trial. And you can see you get the false positive here. This is the psi mapping is the deep MRI. The phi is another state-of-the-art method not based on learning, which is not immune to this, but it does not in any way introduce a false positive. You can see that there's artifacts, but this is not in any way comparable to essentially getting this substantial false information. You can do the same thing with AUTOMAP. I should say, however, that the perturbations may yield vastly different results depending on the different networks. The AUTOMAP one here, this is the original image with tiny random noise, Gaussian noise, and it's so small that it's hard for the human eye to see it, yet it has dramatic impact on the actual quality of the image, and the state-of-the-art method does not suffer from this. And as I said, this is one trial of Gaussian. There's no worst case scenario. This is one trial of Gaussian noise. Anyway, so that's what you see. The theorem does describe, in some sense, what you actually see in the real world. And why does it happen? Well, it's simply the cardinal sin that I mentioned. If you recover things that are too close to the null space, you only need to do this now on 2 elements, and then you get the instabilities. And what happens, obviously, is that when you train, you're getting this on a lot of different vectors for which you really don't know. You need to understand something about the kernel of A to avoid this. And if you're interested in more details, have a look at the paper. We argue why this is not easy to remedy. You can try regularizations on this, and we show that the regularization parameter becomes unstable. You can change your training data a bit, shows that that process is also unstable. And essentially the lesson that you get is that you can't do anything with this unless you have some awareness of the kernel. And that's what we call kernel awareness. And I'm going to say a little bit about what that means, typically, for example, in compressed sensing. If you've never heard about compressed sensing, that's completely fine. Compressed sensing is a technique for doing inverse problems as well. But for it to work, you need to have some assumptions. And the kernel awareness of this is what we call the robust null space property. You can sort of taste the word null space. It's about the kernel. I'm not going to get into the details here. The point is that if you have this robust null space property, you can recover S-sparse vectors. S-sparse meaning you have only S components in the vector that is non-zero. And if you solve this convex optimization problem here, and you have this robust null space on your matrix, you're good, and you can get this nice error bound, which is in terms of the noise parameter. And that's the whole point. To be able to do these kinds of reconstructions, you need to have some information. And the point we're trying to make is that if you don't use any information about the A, there's no way that you can create any stability out of this. You need to have some assumptions. And the big question is, you need to find what they are based on your M1. So a reasonable question to ask then is that if we have this type of kernel awareness, can we then essentially do things? Can we now compute neural networks for these compressed sensing problems? And the fact is that you can, but this is very delicate. And mind you, we just showed the theorem before that even these very basic mappings that are the essence of compressed sensing, there exist neural networks that can do the job, but computing them is a whole different business. And what that says is that you need specific conditions for this to work. Otherwise, there doesn't exist any algorithm that can do it. So what you can do, if you have robust null space property, there exists an algorithm that can do this. So it can create a neural network. So my input now is a matrix that has the robust null space. N here is going to be, as you see in the theorem here in the estimate, it's going to be an error parameter. And now I can get something, a neural network, which is not trained at all. It's completely constructed. There's no training data. And if I take my y's and I compare that to the x's, it will recover it If it's completely S-sparse, this guy here is going to go to 0. Here is the noise parameter, and this is a part that's going to tend to 0 if I let n grow. I should say, however, this is a very simplified theorem. There's much more juicy stuff in this paper that's coming soon, and you can do this with much other different models, not just sparsity, but other models as well. Okay, and now you can test it, because I promised you that I didn't do any worst case scenario tests on other methods when we compare this with AUTOMAP. So this is the experiment that you've seen before. This is the AUTOMAP, the Nature paper method. And here's what happens. You have the original guy. We create worst case scenarios. These are the small perturbations, which give you really, really, really bad outcomes under the neural net that is trained. And see what happens when we do exactly the same exercise on the one that was constructed from the previous theorem. And that's not a surprise now, because actually this matrix A in the experiment in Nature is a wonderful matrix. And this shows the irony that this here is completely stable, just as the theory says. But this method here is completely unstable simply because of the methodology itself, not the A. The A is great. So when the A is nice, then you can actually do things, and you can see this in practice. What you can also see here is that the actual constant, the local Lipschitz constant of this image here, is not bad. It's not 1. You see that there is a difference, but it's not great. The difference is not large. So what that constant is, it's somewhat bigger than 1, but, well, I'm not going to speculate, but it's certainly not a big one. Anyway, I'm going to wrap up with a couple of other sort of methodological observations. And the first one that I want to use or ask is, can we now use the fact that you have the robust null space property? And can I, with that, take one of the sort of state-of-the-art methods, if you will, in deep learning, namely adversarial training, to be able to train and get the same results that I got when I just constructed the neural network? In other words, I want to test the current methodology, which is the basic ones in deep learning, and see if it can actually solve this problem. So adversarial training is essentially done with this min-max game. You take the max here, and that max is going to be sort of the adversary that seeks the worst case scenario. And you want to train your neural network so that you can make it robust on that. But it's not just good for robustness. What you do is that you essentially also enhance, in some sense, your data set, because you can now talk about the whole ball around it. And I'm simply going to assume that I have an oracle that can do this. I'm not going to do this numerically. I assume I have an oracle that can do this. I also have an oracle that can do this. And now we have a theorem for this, and I must apologize. It's called a theorem because it's not completely done yet, but the message is there, and I will report on the complete theorem on this hopefully pretty soon, but I couldn't resist showing you sort of the bigger picture. And here's the paradox I want to show. If you have a robust null space matrices, then you can create neural networks through an algorithm that can compute them, and you can do this even in polynomial time with a very small exponent here, and you can do this to arbitrary precision. But if you want to try this now with adversarial training on this here, if your network is expressive enough, you will actually need, in this case here, 10 to the 80 data points if your sparsity was S equals 25, and n, the dimension of the space, would be 256 squared, which is a very, very typical dimension that you see in imaging. And 10 to the 80 is the magical number. This is sort of the part of the folklore on the estimates of how many elementary particles there are in the universe. So if you're getting into 10 to the 80 data points, even to get 0.1% success rate, you need a different or a parallel universe to succeed. So now you can ask, well, S-sparse vectors, are they of interest in imaging? Not really. It's not something that you see on a daily basis, but you do see them on specific applications. For example, NMR spectroscopy. If you Google NMR spectroscopy, you'll see this image here that I just nicked from the web. And these are typically exactly the kind of signals that you try to recover from the Fourier transform in NMR. exactly the sparse ones. And you can try this. Take your favorite random Gaussian, which will have the robust null space. Try to train this with a neural network, and you'll see that even with 10 to the 80 data points, you will not succeed. You can try this at home. I've tried it. Well, not with 10 to the 80, but it gives you garbage. And with that limitation on what you can do, then we need to essentially ask the question, which inverse problems can you essentially now handle with the current deep learning methodology? And I'm gonna speculate a little bit here. I'm not gonna make any mathematical claims, but what I want to point out is that the world is actually full of sparse-ish problems. And suppose now, for simplicity, that my problem in MRI is to locate brain tumors. I put 5 of them here at random locations. And I'm simply asking, will I be able, with the current deep learning methodology, to create a neural network that will with certainty tell me that where these brain tumors are? And I'm not going to give you an answer to this now, but I am willing to bet a lot of money that won't be able to prove that you won't be able to do this. And it's going to be the same sort of combinatorial nightmare issue that is needed to show the other results. And it's important to emphasize this because here is an example for which you see neural networks that have been trained on something. This has been trained on ellipses. This has been trained on standard brain images. This has been trained on knee data. And if you add now some details that it hasn't seen, you get garbage. It either washes it out or you get really, really poor performance. I just want to show that you can do this with other methods. So it's not that the problem is impossible itself. And then the argument is usually, oh, of course that happens because you haven't seen it. It's not been in the training set. Indeed. The question is, can you actually train the neural network now and get these details? Because what could very well happen is that your training data is going to be on the order of 10 to the 80 to solve that problem. And that's going to be a hurdle. And that also leads to the question about how do we assess the performance of deep learning methods in inverse problems? Is PSNR good enough? Or do we actually need to have some testing about the success of what it's supposed to recover? For example, in this case here, certain brain tumors. Anyway, I'm going to wrap up because I'm out of time. I just want to say that we feel that we need a foundations program. We need to know the boundaries of AI for safety and security reasons, which I have tried to argue. It's going to be good to know this because it actually saves time. You want to know that you cannot create gold from the get-go. And by knowing the boundaries of what can potentially, or the boundaries of the methodology, it also aids us how to create new and better methods. And my strongest personal motivation on this is I simply want to know, and I think that that is something that a lot of people feel, and I think that also echoes the sentiment from Ali Rahimi that we want to know what's going on. And I'm going to end with a slide here, which is shameless self-promotion. Ben and I have a book out in, it's actually going to copy editing very soon. It's going to be out in Cambridge University Press. It contains a lot of the stuff that I've talked about today. So with that, I thank you very much for your attention and say to the people out there, please join the Foundation's task force. It's a lot of fun. And thanks so much for your attention.
Thank you very much, Anders. That was a wonderful talk, and thank you to Matthew Colebrook as well, who was working hard on the chat, answering questions. So I'd encourage anyone who has questions now to sort of ask them in the chat. I'm not sure. I think I'll probably just try and read the questions as they come in rather than unmuting people. That will probably go wrong. Maybe whilst we wait, I can ask. I had a small question.
Shoot.
And that's so the results, as I kind of understand them, they kind of assuming that the neural network is trained to perfection. So I guess there's maybe two things one can sort of say here is that if you add regularization, then you know that one going to get zero cost, but also you've got kind of implicit regularization that if you stop your training early, do these help you or do they harm you, or are they Can you say anything?
Excellent question. So first of all, on the lower bounds that are universal, that doesn't help. The universal bound says there's no way out of this. You can't do anything. Now for the other ones, for example, this one here, this is simply, this happens here for any lambda. So the regularization is not helping. It's a very simple argument for this. The point is that when you create a neural network that does this, there's an implicit information about the sparsity. That's what I'm interested in. In other words, the code or the algorithm knows this. I'm writing it up for it. When I'm trying to solve this problem here, the neural network has no idea what it's trying to solve. It just tries to map the y to the x. And I can do that. But there's so many s-sparse vectors out there. I get more than 10 to the 80 of them. So if I'm going to actually try to interpolate this in any way to have any success on this, I will need to see so much data, because otherwise I'm going to fit other things, because the neural network has no idea what I want it to do. And this is really crucial. And I'm not saying that we shouldn't do these things, but probably will happen in the future is that there's going to be hybrid methods for which you do something like this with some kind of learning. But you need to have some kind of awareness on this. So this method here, if you will, the algorithm that constructs that neural network, uses particularly the fact that A has the robust null space property. This problem here has no idea what that A could be anything. It simply tries to minimize. And that's why there's no way that you can do this. So, as I said, try this at home. I've had many students actually playing with this. See what happens. And you get complete garbage, simply because you don't have enough data. And so you can try and do this back and forth, but essentially this statement here is true for any lambda. So early stopping, whatever, that's not the case. You will be data starved. And we're back to essentially the second component of that instability, or that lower bound theorem, is that there will be cases for which you won't be able to solve because it's simply going to be too data intense.
Okay, thanks. There's a few questions on the chat that we'll try and okay, so someone's asking, have you tried a qualitative version of robustness?
Say that again,
A qualitative version of robustness. Let me motivate this question. Anders, very nice.
Oh, hey, good to see you, Human. How are you?
Good, thanks, Anders. So let me motivate this question. In Bayesian inference, you have two notions of robustness: the classical one and the qualitative one. So in the classical one, you fix the data, you vary the prior, and you look at variations of your posterior values. And there you have lack of robustness, you have brittleness. And the qualitative version is as follows. You randomize the data with respect to the data generating distribution. So your posterior values become randomized through the data, which is randomized by the data generating distribution. And then you can look at the stability of the posterior distribution with respect to variations of the prior. And if you do that, you will see that you get some stability, but you also get a trade-off between robustness and stability. You realize that these two things are conflicting requirements. You cannot
Indeed.
get both at the same time.
Absolutely. So, okay, so to answer your question, all of these things are worst case scenarios. And so there's secretly sort of an optimal thing that I've done here by saying that it's the worst case. So to answer your question, none of these results here are in a probabilistic sense. Well, except for the algorithm doing it. But it's not, as you say, if there's a distribution that you draw from. That's completely correct. That doesn't mean that you can do the analysis in that case, but that this is not done in this way here. So that's absolutely a great point. And I also want to say, you're absolutely right when you say that there's a trade-off between stability and performance. And in some sense, you can see this, well, for the inverse problems, immediately in this case here, because there will be certain cases that you are not allowed to get good performance on, because if you do that, you get the instability. But there will be certain ones that you are. And you could also make the argument that, okay, if I have now a distribution for which this happens only in few cases, you'll only have tiny little cases for which this is happening. And then we'll go back to this estimate here. These things might be small. which is exactly what you're saying. So I'm not suggesting that there's not other ways of interpreting this, but there will always be, unless you have the kernel awareness, there will always be a probability for which this is going to happen. The question is how big it will be. And that will also be a trade-off with the performance, which is exactly what you're saying. So that is spot on.
Thank you.
Someone asked if you could clarify their understanding. And I think they're correct, but I'll put the question to you. So they say that the classification result seems pretty Gödelian in the sense that you'll always have some set that will frustrate your neural network, no matter how lenient you make the accuracy desired. So is that the correct understanding of your results?
Say that again.
That you'll always have some set that will frustrate your neural network, no matter how lenient you make the accuracy.
Yeah. If this is related to the theorem about computability of the neural networks, then it is about the neural network that you're trying to compute. It's not the one that exists. The paradox that we're trying to emphasize is that there exists a good guy, but if you're going to try to get it with an algorithm, you're not going to succeed. So there's two neural networks. There's the good guy, for which we know exists. So we're not trying to set this up so that there doesn't exist a good guy, and of course then there's no algorithm that can give it to you. The paradox is that there does exist a good guy, but you can't get it. So there's two different neural networks that we're talking about. So is the question now about the one that you're trying to compute?
I expect. Okay.
Maybe we can ask Wen-Jiang to ask the question himself. I think it seems to be clarified now.
Okay, awesome.
Yeah, so basically, it's like there exists this neural network, but then you'll never be able to compute it, right? You can only get...
You will never be able to compute it to the choice of accuracy that I have chosen first. So the irony is that you will be able to compute it to k-2 digits. That's a good thing. But you cannot do better, or you can get k-1, but then there will be cases for which you're going to be essentially data starved. And if you are greedy and want it for k, then no algorithm can do it.
Right, so you'll never actually get so that basically establishes a very hard limit.
Yes, absolutely, yeah. But the point is that this theorem is bittersweet. It doesn't say that everything is bad. It says that it's incredibly complex. So in other words, if you, in application, needed this theorem, needed your neural network to 4 digits, you might be actually able to do it. But if you needed 5, you might be able to need 10 to the data points. And if you needed 6, you won't be able to do it. And that's what we're trying to say with this theorem, that this here is incredibly subtle.
And this is universal to any sort of way you try to compute the neural network. But if we're not doing a neural network at all, you might be able to.
Yeah, so the point here is that actually I should have said this existence when I say here an algorithm. It can be a BSS machine. It can be much more powerful than a Turing machine. This is universal for any model of computation. And I could even put in an oracle on it that could solve the halting problem. It's not going to help you.
Okay, thank you.
No problem. Thanks for the question.
So I had another question.
Please shoot.
And we're talking about artificial intelligence here, yes. But obviously, to an extent, the doctors who interpret MRI images are are neural networks trained on very finite data sets by experience. So would this mean that doctors will not always recognize things, or do you think that this means rather that we don't see such adversarial examples in practice?
So this is a profound question. And that's why I want to go back to this paradox. Because we don't assume necessarily that the brain works like a neural network. The brain may have an algorithm. So in certain cases, and I'm now just completely thin ice because I really don't know how the brain works. The question is this. Now, there could be tasks for which essentially the brain works as an algorithm, which does something. So like in this case here, there's an algorithm that can do it. But if you try to do it in this way, you're not going to succeed. So the point is that the brain could have been trained in a different way. It doesn't say, what this theorem here says, it doesn't say that you cannot do this with any other AI method. It says the standard methodology is going to fail, which is paradoxical because there exists another way of doing it. So that doesn't mean that if, you know, the doctor is being trained or uses some kind of a way of recognizing that the doctor is going to have the same lower bound. Does that make sense? This is just says that this particular methodology is going to fail, which is, by the way, state of the art for deep learning. You can cook up maybe tomorrow where you say, Anders, I have a really clever way of not constructing it like you do. It's really learning, but it utilizes the knowledge that it has the robust nullspace property. And now I get the same results that you do. That could happen. So what I'm saying is that this is only for that methodology. So to answer your question, we don't know what the brain does, but the doctor may very well have another deep learning algorithm, you know, behind its learning. Did that make sense?
Yeah, thank you.
Yeah.
So I have a question, but hi Anders.
Oh, hey, Felix.
I somehow missed the answer to the preceding question, so it could be that this was exactly what was already asked. So in this question with the 10 to the 80 points,
yes.
What are you saying? Are you saying that always there is a minimizer of this thing which has a bad success rate, or are you saying that each minimizer necessarily will do badly if you don't have enough?
Yeah, so the argument that I'm trying to say is that if n is expressive enough, and if I see too few points in this, then I'm going to have a lot of other minimizers of this problem here, which are not going to interpolate the data. So in some sense, what you're trying to do is that you're trying to fit some data here with a neural net. And if I don't see enough of these things, I need tons of these sparse things, because if I'm now outside of that, I can have some neural networks that really doesn't interpolate. And it solves this problem here on that data set. And the point is that the neural network and this methodology does not know that I'm actually seeking sparse vectors. I've just put that in and says, that's what I want. So unless you feed that in, you will have tons of other minimizers of this problem here for which you're not going to get the right answer. And then you could have said, oh yeah, but you know, but in this case here, you could happen that you get the good minimizers as well. But then my argument is, but how do you know that it's actually the sparse that I want? If I show you now essentially 10 to the 20 data points that are sparse, but what I'm actually interested in is those 10 to the 20 that are sparse, and then something else. That's the structure I'm interested in. That's the true solution. So my point is that if you were just giving the neural network this information here, there's no way that it can actually understand that this is what it is. And what I'm trying to say is that that bit of code saying, I want S sparse, that's essentially inherently in how this algorithm is designed. So if you're going to do this with something different, you have to let that optimization problem know what you're interested in, because otherwise it simply needs too much data to be able to understand what you want, if that makes any sense.
Okay, we have another question.
Please.
Okay, so I'll just read this out. So, universality result holds for any metric. Could the approximation estimate change by choosing a more suited metric for each problem?
So there's a universal metric for all of the statements. And since the metric, this here is for a finite dimensional problem, then the norms are equivalent. So that's true, but I choose the metric first, and then, so let's just go back to this. It's a very good point, actually. You need to really get the details here. So what it says is now, I choose my, oh, right, okay. Actually, you know what? I should have, in the formulation of the theorem, I should have chosen the metric first because before I choose the K to make this. This is actually great. Whoever spotted that, I'm going to make an acknowledgement in the paper. It should be reversed. Choose your metric first and then choose your K, if you see what I mean. But it's not going to change that. But yes, choose your metric first and then choose your K. So the point is that you're not allowed to choose your metric after you do that, if that makes sense. But it's a good point, yes.
That might be all the questions we have. If I have missed a question, please ask it very quickly. Yeah, otherwise, I'd say let's thank Anders again for a very nice talk, and I'm very glad you could join us.
Thanks so much for having me. I really enjoyed it. And a lot of great questions.
So just ask when where the talk will be uploaded to. You can get the talk from through the website, and it will be hosted on YouTube. It will be in the next few days. We'll upload it. I guess if you just check back on the website later this week.